Okay, might as well get started. So, once again, here we are. This is Math 152, Section 4, Professor Ellis's class. I am your SI Jet Work. And today I will be doing some example problems regarding parametric calculus and an introduction to polar coordinates. So we've already covered a fair bit of parametric calculus with derivatives, but we haven't had any experience with integrals yet. And there's a special formula for parametric integrals. If we have a function in f okay. So if we have a function f of, let's say, t, which is responsible for maybe our x value, and we have some function g of t, which is responsible for our y value. It's important to remember the two formulas. First of all, the area bounded by this curve is equal to the integral from alpha to beta, the bounds of integration, of g of t, f prime of t, dt. So basically, take our y function, multiply it by the derivative of our x function, and then integrate it with respect to t over our bounds. Using a similar formula, we can calculate the arc length of a given curve. Again, integral from alpha to beta, not necessarily the same alpha beta, these are just representative bounds. And that will be equal to the square root of f prime of t squared plus g prime of t squared dt. Now, having a square root like that, a lot of your integrals will get a little messy, a little bit unnecessarily complicated. On a quiz or an exam, you typically won't have to solve for those sorts of things, but it's good to know how they work. Okay. So now that we have that information, let's take a look at an example problem. Say the parametric equation x is equal to t squared minus 2t, and y is equal to, say, square root of t. And we want the area bounded by this curve and, let's say, the y-axis. So x equals 0. So in order to find our bounds of integration, we first set our parametric x equation equal to 0. So we'll have 0 is equal to, and I'm just going to jump ahead and make this easier to solve by factoring out t. So we'll have t times t minus 2. Very simple to solve for t. It's going to be equal to 0 and 2. So we now know our bounds of integration. Integral from 0 to 2. And now we take g of t, in this case the square root of t, multiplied by f prime of t, in this case x prime of t. So we'll have 2t minus 2 with respect to t. Okay, so the easiest way to do this is going to be to distribute the square root of t, or t to the 1/2. So we'll have an integral from 0 to 2. T to the 1/2 times 2t is going to be 2t to the 3/2 minus t, 2t raised to the 1/2. All right, now it's just simple power rule integration. So we'll have 2t raised to the 5/2 over 5/2 plus, plus negative 2t raised to 3/2 over 3/2, evaluated from 0 to 2. Okay, so we'll plug in our 2, we'll plug in our 0, subtract what comes out. Our final answer will be approximately 754. That's just done by plugging in 2 to the 5 halves times 2 to the 5 halves, yada, yada, yada. Just evaluate the integral. Okay. Well, let's take another look here. Another problem for you. Same thing. I'm just going to find the area under a curve. So this time we're going to say that x is equal to 1 plus e to the t. And we'll say y is equal to t minus t squared. We want to find the area bounded by this parametric curve and the x-axis, or line y is equal to 0. So same as before, get the bounds of integration. Our parametric y equal to 0. So 0 is going to be factor out of t, 1 minus t, and our t will be equal to 0 and 1. So, plug this in, integrate from 0 to 1. Our g of t is going to be t minus t squared. And multiply this by our x prime of t, e to the t, and take this integral with 2. Now, we're going to distribute this e to the t, and we're going to notice a familiar pattern for integration by parts. Now, we're going to have to do 2 separate integration by parts, so I'm going to split this integral up for convenience sake. So we'll have the integral from 0 to 1 of t e t dt, minus the integral from 0 to 1 of t squared e to the t dt. Okay, so first and foremost, we will solve our first part. So let's solve our first integration by parts. We'll set u equal to a term that will cancel t. Set dv equal to e to the t dt. Integrate, derive du to the dt, and integrate v to get e to the t. So this integral will be equal to t e to the t minus the integral of e to the t dt, which we all know is just e to the t. Okay, so now let's look at this second part. This is going to be a 2-stepper, but it's okay because we've already solved for one of our parts. U is equal to t squared. dv is equal to e to the t dt. du is equal to 2t dt. And v is equal to e to the t. So this integral is going to be equal to t squared e to the t minus integral of 2 times t e to the t dt. Now we already solved for the integral of t e to the t in our first portion, so we'll just be able to copy that down here and multiply by our constant 2. It has no bearing on the n besides that fact. We'll have t squared e to the t squared e to the t minus e to the t minus, we'll have t squared e to the t minus 2, I'm sorry, that's not squared. It's just t e. Give me a moment to calibrate this. Let's see if that works better. All right, trying this again. We're going to have t e to the t minus e to the t times, minus t squared e to the t minus 2 t e to the t plus 2e to the t. Okay, so that's our integral, evaluated from 0 to 1. Plug all that nonsense in, we'll have a lot of e's and a lot of zeros canceling out with the 1s and zeros. But it will come out to 3 minus e. So a little bit more complex of a problem, but nothing we haven't handled before. Now I'd like to take this time to set up an arc length problem. Like I mentioned before, most of the time we'll just be setting up arc length. I'm probably going to try to solve one a little bit later, but on a quiz or exam, it would just take you too long to integrate, and that's not really what we're testing for, so a setup would be sufficient. So let's say we have the parametric equations. X is equal to t squared minus t, and y is equal to t to the 4th. And we want to know the arc length on the interval 1 is less than or equal to t is less than or equal to 4. So as we're just doing the setup on this one, all we really need to do is remember the arc length formula, which will tell us that our arc length is going to be the integral from 1 to 4 of the square root, this is important, x prime of t. Now what's x prime of t? Derivative of x with respect to t. So we'll have 2t minus 1 squared plus dy with respect to dt, which is going to be 4t to the 3rd squared dt. So this is going to be long and cumbersome and unnecessary. Why that is the only answer we need for now. This next problem, we are actually solve an integral to completion, especially properly so that the integral is feasible. We'll say that x is equal to 1 plus 3t squared. Y is equal to 4 plus 2t to the 3rd. And we want to know the arc length on the interval 0 less than or equal to t less than or equal to 1. So, again, we take our arc length function, setting the integral from 0 of square root of x prime of t. So 1 will be removed, we'll have 6t. Plus 4 will be removed, and we'll have 6 squared. T. Evaluate what's on the inside. Integral 0, 1, square root of 36t squared plus 36t 4th t. Sorry, the smart board's a bit temperamental. Not sure why. So try this again. 0 to 1 square root 36t squared plus. We have 36t to the fourth dt. We can see very clearly we can pull the 36t squared out, which will factor to be 6t. The integral from 0 to 1 of 6t square root 36t squared has been removed. 1 plus t squared dt. Okay, so this is just a simple u substitution. U is equal to 1 plus t squared du is equal to 2t dt, multiply each side by 3. Results we want. So we'll have 3, the integral 1 square root u du, which is going to be equal to 3 times u to the 3 halves over 3 halves, evaluated from 0 to 1. Plug our u back in, and we will have 2 times 1 plus t squared to the 3 halves, evaluated from 0 to 1, which will give us 1 plus 1 is 2, to the 3 halves to the 5 halves, minus 2. And I believe this equates to, let's see here, we've got 2 square roots, 4 square roots, that'll be 2 root 2. Okay, this is simplified to 2 root 2 minus 2. That is the final answer for the arc length on this interval. So, not too bad. Sometimes these problems will work themselves out like that, but again, most of the time, it won't really be our concern. Just wanted to make sure you had experience with that. Now we're going to move on from parametrics. I think we've covered enough of it. And we're going to start covering polar coordinates. Now, polar coordinates are a little bit scary, a little bit intimidating the first time, but if you remember your basic formulas, all will be well. So always remember, x is equal to r cos theta, y is equal to r sine theta, and the tangent of theta is equal to y divided by x. That was strange. X. Okay, so with that in mind, we are going to convert a few equations to polar form. So let's say we have the equation x, y is equal to 4. So in order to get this in polar coordinates, just make the appropriate substitutions. We'll have r cos theta, r sine theta is equal to 4. R squared is equal to 4, and dividing by the sine cosine, we will have secant theta, cosecant theta. So our parametric equation for this, r is equal to the square root 4 secant theta, cosecant theta. Simple. Nothing difficult about that. take a look at another one. So our equation is x squared plus y squared is equal to 2x. What are we doing? Well, this is an interesting. It's important to remember x squared plus y squared is a little trick that we can pick up on here. Let's examine the definition of x squared. We would have r cosine squared theta. Add that to the definition of y squared, r squared theta. Pull the r squareds out, and we have a very familiar identity. Sine squared theta plus cosine theta, which we all remember is just equal to 1. So whenever we have an x squared plus y squared, we can make a substitution for it immediately and call it r squared. And we set this equal to 2r cos theta. In this case, one of the r's will cancel, and we're left with r is equal to cos theta. Polarization of a basic equation. I'm going to do one more, and I think we'll be good for the day. It's time without the identities right there. Y equals x. What to do? Well, we remember what y is. R sine theta. Remember what x is. R cosine theta. Our r's will cancel out. And to simplify this, we're going to say tangent of theta by the cosine is equal to 1. Now let's solve for theta since we don't have an r to solve for. Theta is equal to the tangent inverse of 1, which from our unit circle, we can remember that theta will be equal to pi over 4. Now, I realize that there's another part to this. Theta can also equal 5 pi over 4. So why don't we include that? Well, when we're working with polar coordinates, usually we bound our domain of thetas to avoid any sort of confusion. So if we were going to express 5 pi over 4, we would instead say negative r taken with respect to pi over 4, which would look like this. So we have our pi over 4 angle, we've got our r, and if we want to express 5 pi over 4, which is in this direction, this is just negative r in the same angle, if that makes sense. Hope you can see that. So that'll be it for today. I think tomorrow we'll move on to a little more complicated polar information. So with that in mind, thank you for coming and have a great